Okay, welcome back, everybody. This is not a lecture at all. I have some slides left, but I have no intention of using them whatsoever. There were many, many questions in the talks and many questions that I didn't get around to answering, so this is just an opportunity for you to ask anything about physics, and if I don't know, I'll say I don't know, but I'll otherwise try to answer. Let me start off with a confession. I said something stupid and wrong at the end of the last lecture in a response to a question about neutrino masses. I said there are two ways that neutrinos can get masses, what's called a Dirac mass, what's called a Majorana mass. That was a true statement. I mistakenly said that the Majorana mass does not involve the Higgs field. That was just wrong. I had a brain freeze. But both of the ways in which neutrinos get masses involve the Higgs field. Plays a role for both of them. All right, now the floor is yours, please. I am happy to answer any question at all, and I will start here. Yes, please.
Okay, so yesterday we talked about the Higgs and the Dirac equation, and we had a potential function for some value of the Higgs field, and it was like some parabolic shape. And you said it condensates in the positive region, right? Is there any physical significance or reasoning why we drew it like going into the negative or past zero?
Yeah, so it's yet another of my many lies. Let me... chalk here, good. My artistic skills are not great, so bear with me. This is the potential for the Higgs field. And this is phi, and I drew it like this. And the lie is that phi is actually a complex number, not a real number. And so you should think about this as being the real part of phi, the imaginary part of phi coming out of the board. And so what's really going on here is you want to draw a three-dimensional potential, which is where I'm beginning to get nervous. So the minima, which looked as if there were two minima, there's actually a ring of minima that sit at the bottom. So it's sometimes called a Mexican hat potential. It comes down, it goes up like this, and then there's a ring along the bottom. So, like turning a wine bottle upside down. And so the minima is here. There's various places on the ring that the Higgs can sit in the bottom. It doesn't matter where it sits, you get the same physics for all of them. Okay. Niba, please.
Hello. We are in 2023 now. In your opinion, what are the most important and fundamental questions and problems in particle physics that has not been solved yet, but the timing for facing it is for now or near future, so our summer student or maybe new future physicists should actually be familiar with it?
So I think I understood. Is the question, what are the most important problems in physics that you personally can solve? Is that...
No,
Yes, okay.
We have to get familiar. And timing for facing is now, not, for example, a future 100 or 20 years ago, later.
It's a fantastic question. I can tell you what the most important problems in physics are. I can't promise you they'll be solved in a 20-year, certainly not in a 5-year timescale, but even on a 20-year timescale. So important questions. Why are there 3 generations? Why do the particles have the masses that they have? Why do those mixing matrices have the values that they have? These are questions that have been appreciated to be important for somewhere between 4 decades and 8 decades, depending on how you count. I don't think we're any closer now to understanding them than we were, say, in the 1980s. There are lots of ideas, lots of models, nothing that looks particularly compelling. And I'm sad to say I don't really see any new ideas at the moment that mean this is the ripe time to solve that problem. So that's a bit of bad news. It might be that everything I say is bad news. What else is exciting? Things I didn't talk about in the last lecture. Everything that I have spoken about in the last 5 lectures, the standard model of particle physics, the stuff we're made of, comprises roughly 5% of the total energy of the universe. So that's where we are in our understanding. The stuff we understand really well is just 5% of everything, which leaves 95% unexplained. So what is the 95%? 25% of the extra energy in the universe is called dark matter. And 70% of the extra energy in the universe is called dark energy. They both have the word dark in them, which just means we don't see them. We have no idea what they are. That's roughly the translation of the word dark. But they're very, very different ideas, dark matter and dark energy. So let me spend a minute or two explaining what they are and then tell you what the chances are that we may be able to make a breakthrough. So dark matter is some extra particle that we haven't discovered yet. It's an extra particle or an extra field that is not listed in this table of the Standard Model. We've not succeeded on making it here on Earth, which is why it's challenging to understand any of its properties, because we can't do experiments with it. But we can see it very clearly when we look up in the night sky. See it clearly in many, many different ways. The galaxies rotate, they spin around like this. They rotate way, way too fast to be held together by the visible stars that are there. They should just be flying off. So it's very clear that if you weigh galaxies in various different methods to weigh galaxies, the weight of a galaxy is about 10 times or 20 times more than the mass that we see. That extra mass is dark matter, some new particle that's sitting there. You see it when we look at the cosmic microwave background radiation. This is the afterglow from the Big Bang. It leaves a very clear imprint. You see it in the way that galaxies form in the early universe. It leaves an imprint there. There's no doubt at all that dark matter exists. And then the question is, what is it? And it's worth saying that everything we've understood, the 5% of the universe, is this wonderfully complicated, intricate thing that I've been explaining for the last 3 lectures. So there's 25% of the matter in the universe that might just be one extra particle, or might be many, many different extra particles which have just as interesting interactions as the ones we see here. Might be many different sectors, none of which know about the other ones. So the big sort of billion-dollar question is the following. We know that dark matter interacts through gravity. That's all the evidence we have is because of interactions through gravity. So the hope, the dream, is that somehow dark matter also interacts directly with the particles in the Standard Model through some other force. If that happens, there's a chance that we can make it here on Earth, perhaps in colliders, perhaps cosmic rays are raining down upon us and creating them. So there are many what's called direct detection experiments going on in dark matter, trying to see if we can create it here on Earth. I don't know if these are going to be successful or not. What happens is you just push the boundaries of how sensitive these experiments can be, and you push and you push and you push. At some point, the hope is that you would actually find dark matter and be able to explore its properties. So the ultimate hope is that in some number of years' time, and I can't promise you how many that number is, someone will stand here and give a lecture on the Standard Model, but that table that I put up will include a whole other part, which is the dark matter sector, and we will understand how that interacts with the Standard Model. So in terms of exciting things in the future, there's no promise it's going to work, but it's sort of clear that there's something out there that we should be understanding we don't currently understand. That leaves the 70%. The 70% is weird. The 70% is called dark energy. It's sometimes called a cosmological constant. And it is an anti-gravitational force field spread thinly throughout all of space that makes everything in the universe repel from everything else. We have very little idea what's causing this. We can add an extra term in Einstein's equations that models correctly the expansion of the universe. The universe is expanding. We've known this for a century, but the expansion is speeding up over time. That's what this dark energy is doing. So you can add an extra term, but somehow there's no microscopic understanding of why that extra term is there and what it's doing. That, in some sense, is the biggest mystery in physics, just because it's 70% of the energy of the universe. So again, it's clearly a very major theoretical problem, one that we've had now for 20 years and one that we've utterly failed to explain in that time. So that's going to need some new idea about quantum field theory and about what underlies it. So I think with broad brush, they're the big open questions that sit there. And then, of course, you hope for surprises. You hope that gravitational waves discover something that does not make sense from our fundamental laws of physics. Or you hope that something else comes out from left field. That's often happened in the history of physics. So, yeah. Yes, please. Yeah.
So you kind of touched on this, but I was wondering what the implications are for gravitational wave detection for things that are like beyond the standard model, or things like domain walls and things like that.
You know, I think the zeroth order answer to that is probably nothing, if we're honest. Because these gravitational waves are detecting colliding black holes. The black holes that collide are, you know, tens of solar masses or something. So they have event horizons which are of order 10 kilometers. So what's happening is you're smashing together two admittedly extraordinarily heavy things, but you know, the physics is the physics of order 10 kilometers. It's not the physics of order 10 to the minus 15 meters or 10 to the minus 23 meters of particle physics. So, you know, I think the most likely thing is you learn a lot of interesting things about astrophysics. You learn a lot of interesting things about the evolution of structure in the universe, what time black holes form, how they form, and so on. So it's good science. It may not be science that attacks the sort of fundamental, in the sense of microscopic questions in the universe. So that's the zeroth order answer. But again, you could hope for surprises. You could hope that it discovers things that aren't two black holes colliding, that maybe there are cosmic strings or domain walls or some weird structure out there that is then a very, very clear hint that something interesting happened. The other thing it could discover that would just change everything is primordial black holes. Black holes that were left over from the Big Bang or from inflation. That would completely revolutionize our understanding of what happened during inflation, during the very earliest stages of the universe. So again, you know, you have to get a little bit lucky, or nature has to offer a surprise to you. So there are opportunities there, but it could also be that it's just interesting science, but in an astrophysics domain rather than a BSM domain, for example. Yes. So I'm going to move over to this side. Yes, please.
Hi, I had more of a personal question. Like, what is your take on the new phenomena searches that are going on, like beyond standard model searches, like VLL or Z prime model to explain the muon G-2 anomaly? And so basically, what we are doing is we are like doing the search experiment and excluding more and more region. So like, till when? What's the future? Like, what's your take?
So the question is about, you know, anomalies beyond standard model physics, where standard model doesn't quite agree with experiment. You know, I wasn't going to use these slides, but let me just show you. So I gave these lectures 3 years ago, and the very last part of the lecture was, does the standard model get anything wrong? So I went through three things. I went through the G-2 discrepancy, the B anomalies, and some discrepancy in the W boson mass. You know, as is the way with these anomalies, they've basically been resolved since my last lecture. So although it's a little bit controversial, I replaced all of those slides with this one for this year. You know, other people would stand here and say something different. They'd say, well, yes, it's not quite gone away. The RK anomaly went down and we didn't understand the statistics right. But you know, I've been around long enough now where many discrepancies with the experiment have come and then faded away a year later. 20 or 30 of them that have been a big deal and then were not a big deal. And of course, as humans, we get excited. We get excited when we find, you know, what we think is new physics. And I like the mentality. You know, the mentality of particle physics is that we want to be wrong. And there's not many places in society where that's, you know, that's the goal, is to prove yourself wrong, to prove that the standard model is incorrect and that there's something else beyond it. So I like the mentality that drives this. Nonetheless, you know, the lesson from, how long's this place been running? 15 years now, something like this, you know, discovered important things, discovered the Higgs boson. But most of the other things have been confirming the standard model, which is the way science works. It's not our fault or nature's fault. You know, we're just trying to learn better. So my current feeling, and again, I'm probably not the right person to ask because I've never quite worked in this game, and other people may say something different, but from a slight distance, it appears to me that the things that were exciting last year are not exciting this year. Yeah. Yes, please.
Hi. Yesterday you were talking about the G coupling constant with the Higgs.
Uh-huh.
I was just wondering, what are the factors that influence it? For example, maybe like cross-section or charge. How do you like theoretically like predict a value for that?
We don't at all. We go out and measure them experimentally. Yeah. So these things, they're called Yukawa couplings. It's Is this formula that you mean, that
Yeah.
the mass of all particles is related to the Higgs condensate with some dimensionless number?
Yeah.
There are 12 of these dimensionless numbers, roughly speaking. Maybe it's 6. Okay, I can't quite remember. But some numbers, none of them we can predict from first principles.
Okay, so
That's one of the
experimental.
big open questions. We go to experiment, and experiment tells us.
Okay.
Yeah. Yes, please. No, yeah, so the question is, can we definitely say that the right-handed neutrino does not exist? And we can't definitely say that. We don't know is the answer. I think most people feel it probably does, but the right answer is experiment will tell us. So what's going on? It's a singlet. You're right about that. So this object here is an object that does not couple to any of the three forces. Hypercharge, no hypercharge, not strong, not weak. So it's immune to the forces. But the idea is that it would couple to the Higgs boson and to this collection here. So it doesn't couple to the photon, you're absolutely right about that, but it can couple through what's called a Yukawa coupling to the Higgs and to other fermions. And so as we improve our understanding of neutrino masses, and by the way, Nima, for your previous question, I should have said neutrino masses is a place where there's been huge progress in recent years, and it seems likely that we will continue to improve our understanding of that. But as we improve our understanding of neutrino masses, we'll be able to say for sure whether this guy exists or whether it does not. Okay, yeah, please.
So I have a lot of questions, but I'll take one of them. About renormalization, you said you wanted to give a more intuitive way of seeing it rather than, infinite minus infinite equals 2.
Yes.
Can you go a bit further on that? Because I didn't really catch what you meant by this more intuitive way of seeing it.
So when renormalization was developed in the 1950s by Schwinger and Tominaga and Feynman and Dyson and others, it was very much you do a calculation. The calculation gives you infinity. You find a way to subtract another infinity and get a finite answer that agrees with experiment. And it wasn't that they were cheating, but it was dubious mathematics at best. Dubious mathematics that gives answers that agree to experiment to 13 decimal places. So it's sort of an odd situation. But it sort of gave a feeling that that's what renormalization was about. It was a shady process. And that's not the right way of thinking. So the right way of thinking was developed mostly by Ken Wilson in the 1970s, with some precedents, Leo Kadanoff in particular. And they understood the right way of thinking by working with boiling water. So when you boil water, boil water in your pot or kettle. Obviously, it'll boil and it'll turn to steam, and it's a violent process. Everything bubbles. Now put a lid on the pot and hold the lid down, so the pressure is higher. It probably feels more violent when the pressure is high because you're sort of feeling the pressure pushing up. Actually, the difference between water and steam is less as the pressure gets higher. And as the pressure gets higher and higher still, I don't remember the exact thing, but 100 times the pressure in this room, something like that. I'm out, I'm sure. The difference between water and steam disappears completely. And above that, there's no phase transition at all. So there's a special point in the water-steam phase diagram called the critical point. And what happens at the critical point is it's like fractal behavior. So at the critical point, the water is sort of bubbling like crazy. There's bits of steam, bubbles of steam, bits of water. But the structure is a fractal in the sense that as you look to smaller and smaller distance scales, the pattern just repeats itself over and over again. And if you were to treat this thing theoretically and naively, you would just go down to infinitely small distance scales and just see the same pattern repeating. Now, for water, it's clear. There's no infinities in the game because ultimately it's just made of atoms, and so everything is just cut off at the atomic scale. Nonetheless, when you do those calculations naively, the same infinities appear as appeared in Feynman's renormalization of quantum field theory. So the mathematics of understanding water boil is basically identical to the mathematics of quantum field theory. But because it was in the kettle and it wasn't some complicated quantum field thing, you have a much better physical intuition for what's going on here. And it's clear there are no infinities because the atoms, as I said, just replace things at the end of the day. So what's really going on, Wilson understood, was that renormalization is an idea about how things look at different length scales in the universe. That the laws of physics are organized in terms of length scale or correspondingly energy scale. And the equations that you use to describe the laws of physics, and even the concepts that you use to describe the laws of physics, differ as you move from one energy scale to another. Which in some sense, you know, at very short energy scales you describe quarks, and at very large energy scales it's planets moving around. The language you use differs. But even as you move between energy scales, the coupling constants themselves change. They evolve as you go from one energy scale to another. So that was part of Wilson's vision, and the fact that these coupling constants are varying really has nothing to do with the infinities that are there in the calculation. Actually, maybe I'll say that slightly differently. The reason the infinities appear is because you don't appreciate that the coupling constants are not constant. As soon as you appreciate that the coupling constants change with length scale or energy scale, that what was an infinity kind of gets brought into that and the infinity disappears. So done correctly, there are no infinities in quantum field theory, just like there are no infinities in your kettle. Yes, please.
Hi. Yeah. Okay. So I just wanted to jump back a bit to dark matter. Why is it that it's usually considered more viable that the dark matter exists, other than, for example, considering that we don't know something about gravity in that scales?
Yeah.
Why do we not consider those as much as this long-lived particle that could be dark matter?
I think there are a few reasons why we don't. Some are theoretical prejudice, but the most compelling ones are just the experimental data. So when dark matter was first discovered, it was because, well, really, Zwicky discovered it because of globular clusters and using the virial theorem, but the nicer way to think is in terms of Vera Rubin's work about galaxies rotating too fast to be held in place. So given that, obviously you're using Newton's formula, force drops off as 1 over r squared with the mass in there. And you could well ask, why not try to change Newton's formula rather than postulate that the mass is higher? You certainly can, and there's a huge community that try to do this. But the evidence for dark matter is so much greater than just that. So even in the same picture, there are this bullet cluster where, have you seen this picture? If you Google bullet cluster, there's a red bit and a blue bit. But two galaxies have collided, but the dark matter didn't collide, and it just kept on moving. So the mass of the galaxy, most of the mass of the galaxy is in dark matter, and so is way outside where the visible mass is. So that's very compelling. The single most compelling thing, though, is the cosmic microwave background radiation. So the cosmic microwave background radiation has some peaks that look like this. I don't know if you've seen it. The relative height between the first peak and the second peak tells you exactly how much matter was charged and coupled to photons versus how much matter was invisible to the photons. And it just agrees with what you get from globular clusters, from galactic rotations, also from structure formation. So there are theories, like I said, that focus on galactic rotation curves. Those theories say nothing whatsoever about the cosmic microwave background radiation. They just don't agree with it. Also, and this is where my theoretical prejudice comes in. We have a great theory of gravity. It's by Einstein. It's astonishingly hard to change that theory of gravity. Many people have tried. It's just difficult because it's already something with this sort of close-knit internal structure that's just just hard to change. Everyone wants to be the next Einstein. Everyone wants to be the person that changes Einstein's equation to something else. The idea that dark matter exists is simply one of humility. There's stuff in the universe we don't know. There's stuff that I didn't write down on the table here. And all the evidence suggests that we should be humble, that we should just admit there's stuff that we don't know that's out there in the universe, the experimental evidence. I did try earlier this year to learn what MOND is. MOND is modified Newtonian dynamics. It's precisely the theory which is supposed to explain dark matter through changing gravity. I don't think there is such a theory. I think there's a cobbled together set of ideas, but there's really no compelling theory for that. Certainly nothing that comes close to the actual theories we have that describe our world. So, I might be wrong, but my take is it's sort of obviously dark matter and not some change in the gravitational dynamics. Please, yeah.
This question, I may have misunderstood you when you said it, but I was just wondering about the Higgs boson and where the Higgs boson is created. Is it just created in colliders? Does it appear naturally? Did it appear naturally at the start of time? If it doesn't appear naturally, how are we getting these couplings?
It's a fantastic question, so let me try and spell this out. There are two independent things going on here. There is a Higgs field, and then there is a Higgs boson. And they're related, but you should think of them as conceptually distinct. So the Higgs field, like all fields, is everywhere. But unlike all other fields, the average value is non-zero everywhere. It's non-zero everywhere in the universe. It's been non-zero for most of the last 13.6 billion years. As you go closer and closer to the beginning of time, and I'll get the numbers wrong, but let's say 10 to the minus 23 seconds after the Big Bang, something like that. It was fluctuating wildly, but after that it's been...
Is that the spontaneous symmetry breaking?
And that's also called spontaneous symmetry breaking, and it's what's sometimes called as the Higgs mechanism rather than the Higgs boson. If you're politically correct, you have to call it the Anderson-Brout-Englert-Higgs mechanism. And if you really want to be politically correct, you have to add Hagen, Guralnik, and Kibble to that list as well. So Higgs is shorthand for, as always, the work of many, many scientists. So the field is everywhere. What's the particle? The particle is a ripple of the field, so it's changing the value of the field away from that average 246 GeV. That, to my knowledge, does not happen naturally, even though there are violent events that happen, collisions of black holes, collisions of neutron stars. I don't know about collisions of neutron stars, actually, but certainly there's no observational evidence that happens anywhere, but it happened here. It happened here when we managed to build a collider that was strong enough to reach these energy scales. It also certainly happened in the early universe. So the early universe was a much more violent event than anything else we have. So there were surely lots of Higgs particles created there, which subsequently decayed. These Higgs particles don't last long. They decay typically to 2 photons.
So then does the interaction that the particles in the standard model have is with the Higgs field to get their mass?
Yes.
Is with the Higgs field and not the Higgs boson?
That's exactly right.
And
yes,
is that due to the non-zero value that it can do that, or is that a thing that all fields can do, interact without the boson?
Sorry, I missed the last question.
Is the fact they interact with the field without the boson due to the fact it's non-zero, or is that a thing that all fields can do?
No, it's due to the fact that the Higgs has this, what I call a condensate, the non-zero value.
The vacuum
that's the thing
value, that allows this interaction without the boson.
Exactly, yes. That's what all other particles interact with and gives the mass, yeah.
Okay, thank you very much.
Very good. I'm going to take one at the back. Yes, please.
So this goes back to when we were talking about the electron, and if we get closer to it, we get the, antimatter-matter pairs.
Yeah.
So can that ever be experimentally proven? And then just in general, what does the lack of resources to experimentally prove something say about our theories of physics?
I can answer the first question. The first question is yes. You know, as you probe to shorter and shorter distance scales, you see explicitly that the fine structure constant gets bigger and bigger. That's, you know, it's maybe a slightly indirect proof, but it's the fact that as you're getting more and more inside that cloud of electrons, you're seeing the true charge of the electron, which is buried inside. That's seen. I put the data on one of the slides for the strong force, but you can find even more accurate data for the fine structure constant if you Google and see how this changes. So it's proven, you know, in that way and in many other ways. Just the whole consistency of the theory is part of it. And then the last question was about the lack of resources, and I didn't quite get it.
It's more so like you were saying like, if we want to discover something, these new particles, but we lack the detector, we lack the technology, we lack the everything, does that say anything about our theories, as in it's like wrong, or as in they're right, or any other possibilities for that theory to exist, if we can't prove it now, or even in the future?
So I'm not really sure I understood the question, but I'll say something and then you can tell me if I've got the wrong end of the stick. So we've got the standard model. We absolutely have the resources to test the standard model, and it's just succeeded spectacularly well. There are many theories that have been suggested for physics beyond the standard model, and some of them have just been proven wrong because they should have shown up at the LHC or at other detectors, and they just haven't. You know that there are various ways to test these theories. The bluntest way, but by far the best, is just to build a bigger accelerator, a more powerful collider. Simply because, you know, this is a microscope, what's going on down there. And if you want to look at smaller distances, you build a better lens for a microscope. But in quantum mechanics, by the time you get to these distance scales, distance is inversely proportional to energy. It's just a fact of quantum mechanics. So if you want to look at shorter distances, which is where these things are happening, you simply need higher energies. And of course, there's, you know, these things aren't cheap, so lack of resources sounds a bit churlish somehow. But, you know, if someone has a spare $10 billion to build the next one, then fantastic, and I hope this happens. People have realized, though, that as you know, the cost and the time to build new colliders and new detectors gets longer, there might be more indirect ways to look at things. So precision experiments, which doesn't mean you actually create the particle there in front of you and you can just read off all its properties, but you might be able to see the effect of these virtual particles beyond the standard model appearing in other experiments. And so there's also a lot of work sort of pushing this precision frontier, trying to understand things there. Did that answer the question partly?
Yeah, partly. I guess like I could use an example where it's like the gravitron, right? What's the particle for gravity that we're supposing?
Yeah, the graviton.
Yeah, so if we need, I think I've heard like ridiculous estimates as to like what size detectors to do this. But like if we're never able to build such a detector, does that say anything about the theory itself? Like,
oh, you know, Freeman Dyson actually suggested that the graviton may, in principle, be undetectable by any advanced civilization.
Yeah, so like that, if it's even undetectable, like what does that say?
Maybe, but maybe not. It sort of just seems one of these speculations that's best had at 2 a.m. after you've smoked something and not really thinking seriously about physics. I made a suggestion about the graviton, which was a little bit tongue-in-cheek in the lecture notes, but my suggestion was the following, that if you look at fossil records, photons were first detected on Earth 550 million years ago, because that's when eyes first evolved. And it took 550 million years to go from the detection of a light to the detection of a photon, which happened about 100 years ago. That's probably a reasonable timescale to go from the detection of gravitational waves to the detection of gravitons. It's as reasonable as any other timescale that I've heard, in the sense that we have no idea. You know, if somebody gave me all the money in the world, I'd still have no idea what technology to build to detect a graviton. It doesn't mean the theory is wrong. You know, if those fossils had come up with quantum mechanics 550 years ago, they would have been right. Yes, please. Yeah.
So to better understand these lepton and quark generations, so like for example, the first generation is our electron, up, down, and then the first neutrino. If they're identical between generations, besides mass, effectively, is there any reason why, in the case of a much higher cosmic background or higher vacuum stability, or whatever the condition requires, we could not construct effectively a modern world out of these particles or some parallel equivalent to it out of the second or third generation? And this is both in the case of including the previous generations, so then you'd have lots of building blocks, or just including the second generation, just the third generation.
So you say construct a world, do you mean make atoms out of them? And
yeah, effectively
like
create stable, long-lived particles that, or up to the point of an atom, or, yeah.
It's the stable, long-lived that's the problem, that these things all decay muon 10 to the minus 6 seconds, 10 to the minus 7 seconds. Things that are made of strange quarks, if they decay through the strong force, 10 to the minus 24 seconds. It's the decay time that's problematic. So in principle, yes, build an atom with muons going around. It should absolutely be possible, but you're going to have it for 10 to the minus 6 seconds. Yes. Yes, please.
Following up on the thing you just answered, is there a reason why some particles are stable and some are not? Like, do you have an explanation for that?
They're the lightest ones that are stable. So it's a bit like Newtonian mechanics, where you have some potential and a ball rolling in a hill. There are lots of equilibrium positions, but if you're at the top of the hill, you're unstable to roll down to the lowest energy state. And if you do the same thing in quantum mechanics and you imagine something like this, even if you're in a minimum here, if it's not the global minimum, it's just a local minimum, you'll tunnel through and go somewhere else. So the game is that ultimately all particles decay to the lightest possible particle consistent with various conservation laws. Conservation of electric charge being the obvious one, but there's others like baryon number, lepton number, and so on. So it's just nature wanting to find the lowest energy state that's the reason. Yes. So many. Yes, please.
Hi. So what makes the right-handed neutrino so much harder to show its existence? Is it the mass? Or?
No, it's because it doesn't interact with any of the three forces.
Okay, and then also, how does dark matter fit in with left and right-handedness?
I have no idea whatsoever.
Thanks.
Yeah. I can clarify a little bit. Particles that are spin zero, like the Higgs boson, don't have a left or right-handedness. They just are. It's the spin half particles that obey the Dirac equation that decompose into left and right-handedness. Beyond that, my previous answer applies. No idea whatsoever. Yeah. But presumably dark matter is made of one of those. Yeah, please.
So I know you've talked about it you've mentioned it throughout this talk, but I was wondering if you can give me an idea of how you would approach beyond standard model physics. Because, I mean, it's something else entirely. It's like we're wandering around in the dark looking for a light switch. So how would we go about probing into this new area?
Oh, I personally don't do it, but lots of my friends do. So given that I want to keep them as friends, there's various ways. As soon as there's a little deviation from experiment, everyone sort of tries to, if they're honest, they try to think what that means. Usually they take the theory off the shelf that they came up with last year and try to shove it to agree with the new experimental results. So usually it's driven by a question we don't know. One of the big questions we don't know is why the Higgs has the mass that it does. That's called the hierarchy problem. I think that question drove research in beyond standard model physics for 30 years with the hope that the LHC would discover the answer to it. And the LHC has not discovered the answer to it. Just didn't discover anything beyond the Higgs. So we still don't know the answer to the hierarchy problem. Some people say it's not a problem. Personally, I think it's still a huge problem. So there's always, I think, some payoff that these people have between some deep, nice idea, something that agrees with some experimental discrepancy, something that an upcoming experiment will be able to check, which of course is important. If you come up with a new theory, you want people to be able to check it. To give you some example, if you go onto the archive today and go to the archive, go to the HEP-PH section, you will discover 9 papers on pulsar timing arrays and gravitational waves at the nanohertz frequency. 9 papers. Why is that? It's because yesterday, Nanograv announced the discovery for the first time of a low frequency, very low frequency background of gravitational waves. It took these people, you have to submit by 7 o'clock in the evening before. So it took those people, the announcement was admittedly about 9 in the morning, so it took them 10 hours. Some of them are 20 pages long. 10 hours to write the paper. And so people jump, when there's something new, people jump on it. Of course, what really happened is they knew that there was going to be an announcement. There's only one thing this experiment could actually announce. So they didn't know the actual results, but they knew that there'd be something big. So they wrote the paper before and then just plugged the results in those 10 hours. But that's the way people work. Yeah. Yes, please.
Okay, so we know that we can compress anything in Schwarzschild radius to form a black hole.
Yes.
But since in theory we can do that, why can't we find the micro black holes here in CERN?
Oh, just because we can't squeeze things to enough energy density. We can't squeeze things small enough. So you're right. As soon as you can push things together with enough energy to get the mass inside its Schwarzschild radius, you have a black hole on your hands. And the question is, what's the energy needed to do that? So we don't really know, but the naive guess, assuming nothing else happens, interesting happens as you go up, is that the energy is the Planck scale. So 10 to the 18 GeV. LHC does 10 to the 3 GeV. So there's still 15 orders of magnitude roughly before we get there. Of course, maybe you heard there was some dreams, hopes, fears that the LHC would create black holes, but it needed gravity to be wildly different from what we think. It was, something of a dream of theorists and one that was not realized in our world. Yeah. Please.
So we said that there's 3 generations, right? And there's multiplets that get created to kind of tie in all 4 of the particles that get made. Yeah. Is there a reason, like in group theory, that we need 3 generations, or is there like possibilities for a 4th one? And then also, like, could the Higgs have other, like, flavors, I would say?
So firstly, yes, the Higgs could absolutely have other versions of the Higgs, and it's one of the favorite games that beyond standard model builders play. No restriction at all on that. 4th generations, no logical reason why there has to be 3. It's an experimental result. Could certainly be more. There's an important experimental result, though, which is that the Z boson decays. And from the decay of the Z boson, you can see experimentally how many neutrino species there are with a mass below 80 GeV or 40 GeV or whatever it is, but a mass below several GeV scale. And you can see that there are 3 species of neutrinos with a mass below a GeV scale. So what does it mean? The spectrum of masses is weird in the standard model. We don't understand it. But if there were a 4th generation, the neutrino masses would be a millionth of an electron volt, a millionth of an electron volt, a millionth of an electron volt, something bigger than a GeV scale. So it would jump by 15 orders of magnitude. Maybe that's the way the universe works, but there's certainly not a 4th light neutrino species because we would have created it. Yeah. I'll go over here. Yes, please, at the back.
Okay. So you said that the universe is filled with the Higgs field, right? So I wonder if there is a correlation between the non-zero Higgs expectation value and the vacuum zero-point energy, right?
The vacuum self-energy being the cosmological constant or dark energy? Is that
dark energy.
Yeah. No. Yeah. And this is the problem with dark energy is that it's the 0-point energy in space, and it has a scale of it sort of depends where you put the Planck masses, but you know, roughly I think sort of 10 to the minus 30 electron volts is the Hubble constant. So that's sort of the scale that we're looking at. Said another way, dark energy kicked in our universe when our universe was about 10 billion years old. Presumably it had been there all along, but it became a dominant component when our universe was about 10 billion years old. So that's the time scale at which dark energy is operating. Everything in particle physics is at a much, much higher energy. You know, it's by many tens of orders of magnitude. The Higgs VEV is GeV, quantum fluctuations, you know, these particle-antiparticle pairs, they're at the scale of the mass of the electron. So there's lots of things in the standard model that should be contributing to dark energy at a level that is many, many orders of magnitude. 10 to the 60 is usually the thing that's faced. 60 orders of magnitude greater than what we actually see. So what's going on here? What's cancelling the background 0-point energy from the standard model to reduce it in such a way? We don't have any idea. You know, I said earlier that I think this is one of the biggest problems in theoretical physics. This is why. Any attempt to understand it microscopically gets something that's so way off that we're just clearly not understanding something deep and important. So another way to say it is that the time scales of particle physics are somewhere between 10 to the minus 6 seconds and 10 to the minus 24 seconds for the strong force. So something like that. The timescale for dark energy is 10 billion years. So how do you write down a fundamental theory of physics to do with particles and such like, so that there's a component that does nothing for 10 billion years and then it takes over the entire universe? That's the struggle in writing down a consistent theory of dark energy. It just seems crazy, but somehow there's got to be a way to link these two. Yeah. Yes, please.
So yesterday you showed us mixing matrices for neutrinos and quarks.
Yeah.
Why is there no mixing matrix for electrons, muons, and taus?
That's a great question, which I just swept under the rug. There's also no mixing matrix for the up quark sector. I just put the down quark sector, and I just put the neutrinos. So what happens here? There's a misalignment between the Higgs and the weak force, but the misalignment is a bit like a bubble in a wallpaper. You know, you can push it in various directions, but you can never get rid of it entirely. So the choice that is made is to make the up sector aligned between the weak and the Higgs. You have that possibility. And to do the same for the electron muon tau sector. So you can always just fix that alignment. And if you do that, the misalignment appears in the down quark sector and in the neutrino sector. The reason you do it is just because that's the simplest to compare to experiments. No deep reason, no deep theoretical reason. But the masses of the neutrinos are very close to each other. So when the misalignment is in there, it's very clear to interpret it in terms of neutrino oscillations. And similarly, the down and the strange quark mass are very close to each other. So when the misalignment is in there, it's very easy to interpret it in terms of decays of certain mesons. But theoretically, you'd be quite able to push it into the electron sector or to the up quark sector and then try to understand, you know, how to interpret it there. I've never tried that, actually. I think it might be an interesting exercise. But yeah, it's put there really just for expediency to compare nicely with experiments rather than a deep theoretical reason. Okay, yes, please.
With respect to QCD, we have the 3 colors beside the 18 baryons and the asymptotic freedom of SU groups. Is there another more deep fundamental reasons why we have 3 colors?
Not that we know of. There's a possibility. So this is an old plot that's kind of gone out of fashion, but I still think it's pretty compelling. So here we've got 3 forces: U1, SU2, and SU3. Electromagnetism, hypercharge, weak and strong. Each of them has a coupling constant associated to it. Fine structure constant, strong, weak. And those coupling constants change as you go to higher energies. So if you're at the energy scale of the LHC, the fine structure constant isn't 1 over 137, it's 1 over 127. And these are the values of the strong and the weak. So that's the values they take way over on the left here. And then you naively extrapolate these coupling constants from the energies that we can currently probe just up to energies that we can't hope to probe using colliders and detectors. And you see, they don't meet, but they almost meet. They're sort of in the same ballpark. So the idea is that perhaps this is some suggestion that the three forces that we see combine together into one unified force. So when people talk about a grand unified theory, this is what they mean.
Except, like we know from the SU groups are the only groups that exhibit asymptotic freedom, and we have 18 baryons that 3 colors are allowed.
There's no simple numerological answer for why 3 and why not something else. The idea here is that up here the unified group is something like SU5, which 5 is 3 plus 2. That's where the 3 plus. Or it turns out SO10 is a actually slightly more compelling one. So there are various groups that contain within them the standard model groups as subgroups. But you know, none of this really answers the question you want, which is why 3. The answer to that is we don't know. Yeah. Please.
So when you were talking about like dark matter and dark energy and how we don't know like where they come from, quote unquote, I guess this is more of a philosophical question, but when do we get to the point where we've decided that we like know where something comes from? Because when we're talking about like, you know, the different fields that make up these forces and particles, like in some sense that's an understanding of where they come from, but in another sense it's like, where do those fields come from? So I guess like when do we decide that we're satisfied with the answer? I guess maybe the answer is never, but like, I guess what's the difference between just saying, okay, we see this energy, like dark energy that's out there acting in this way, like, why is that not a sufficient description in itself just to say, like, to look at its behaviors and say, okay, like, we're done here?
So you answered the question yourself. The answer is never. You're never satisfied. You want to understand the standard model better. You want to understand dark energy better. But that's just the process of science. You know, there was a great theory called phlogiston, you know, but theories of, if I got that right, theories of heat. Lavoisier had a theory of heat about how there was a liquid inside rocks and objects that would flow from one place to another. It was an amazing theory. I mean, it just explained every experiment you could possibly do. Until after 50 years, it stopped, and it was realized that it wasn't quite the full answer, and in fact, later it was realized it wasn't the answer at all. The cosmological constant just feels a bit like that. I mean, you know, we've got some model of it. But there's nothing microscopic about the model. We certainly don't understand anything deeper about it. So I think this is just the story of science. You understand things and model things and describe things the best you can, but you want to keep asking questions because, you know, that yields results over time. Yeah. Yes, please.
So, disclaimer, I'm not a physics student, so this might be a bit simple for some, but this is the question between quantum fields and particles.
Okay.
So the quantum fields are often like visualized as a scalar field that can take continuous values.
Yes.
At what point would you say that like you get a particle or you get 2 particles? Is it all about probability? Or some particles would have to kind of excite multiple fields, right? Is there an intuitive way to, or some way to think about this?
I think not. The trick here is in the quantum of quantum fields. So, you know, naively we think of a field, the temperature field. Every single point in this room has a number associated to it, which is the temperature in that room. A quantum field is not quite like that. Every single point in this room has an operator on the Hilbert space associated to it, and what we call a quantum field is this complicated mathematical object. So once you appreciate that that's the language, you find that the ripples are not continuous changes of the fields, that they're quantized, and the clue is in the name, in the same way that the energy spectrum of the hydrogen atom can only take certain values, the excitations of these fields can only take certain values, and that's why it makes sense to talk about a single particle or 2 particles and so on. Yeah. Yes, at the back.
So, because of you said about the current and following challenges in physics, which is mainly dark matter and dark energy, and because of the slide about the standard model being a pretty good model to satisfy what we know, I started wondering, is there current work being done on trying to unify the fundamental forces of the standard model, like experimental work that we're doing right now?
I didn't hear the question. I know you want to find the fundamental forces of the standard model.
Is there work being done right now to try to unify the fundamental forces of the standard model?
To find them or refine them?
To unify them. Yeah.
Somebody else. Refine.
Unify.
Unify.
Yeah.
Oh, I see. Thank you. Yes, but as I said, it fell out of fashion a little bit. So Georgi and Glashow had not this plot, but had this idea back in the 1970s. This is what unification would mean, that at higher energies, all the forces fit into one. And there were experimental predictions of the simplest examples of these theories that protons would decay after some time. That didn't happen. So, I think it sort of, people pushed it as far as they could in terms of if this idea is right, and the simplest models predict something we can observe, but then they weren't observed. It doesn't mean the idea is wrong. There was no reason those particularly simple models should have been the ones that hold. So that's one way that, like I said, has fallen out of fashion a little bit. The other way, of course, is string theory, which I've not mentioned at all, but that's a theory that takes everything in the standard model and gravity and puts it together in a wonderfully elegant framework that comes with all sorts of extra baggage. So I think Timo is going to come and tell you about string theory later. But if, that's where most of the activity is in terms of unification, I think. Yeah. Are we done? All right.
And thank you very much.
Thank you.
And here's again the QR code for submitting the lecture survey, and you can also do it on your laptop by clicking on the link on the Indico page.